issues, so we're a couple minutes late, but we're good to go, and it's not by the workshop being recorded. So this is a disclaimer.
Yeah, first my apology that my computer didn't connect here to the hotel Wi-Fi, only to EduRAM, but EduRAM is too weak here in this room, so it didn't work. So therefore we have this whole thing here on a Google Doc and not a PowerPoint. It looks like a PowerPoint. So some animation actually don't work, but I will explain the things and hopefully it's understood. Okay. Maybe then we get started. So this here is about an introduction to practical quantum computing. So towards the end, I will get to some quantum circuits, but I will start off with explaining a little bit the difference between a classical system and a quantum system. So no quantum mechanics is required for this workshop at all. So I want to start off with a little intro in case that I have small magnets in a magnetic field. So you see here magnetic fields. This here is a magnetic field. The field lines or the density of the field lines simply represents the strength or the relative strength of the magnetic field. Here you see that you have an homogeneous field or and here you see that you have a variation of the field. Yeah. So let's see whether this is coming up. Yeah. So in homogeneous fields, a magnet will experience a torque, so it starts to rotate. You are using that for all electromotors. In an inhomogeneous field, there's a magnet experience possibly a torque that it aligns to the field, but also a force towards a stronger B field. So for this case, it's going here in the direction where we have more field lines. Yeah, and that we want to use now for an experiment. And for this experiment, we have a setup of an inhomogeneous magnet where the south pole or the upper part has a smaller area than the lower part. Yeah, and therefore field lines in the upper part are more dense than in the lower part. So that means the magnets will experience a net force. At the same time, they try to rotate a little bit in order to align to the magnetic field. Okay, and for that, we have here this, actually, if this is working, let's see. Then we can actually use this stuff here. So this is here an animation which I wanted to split into several parts, but let's simply do it. So this shows these magnetic, the top and the bottom pole shoe, and a little magnet, so a tiny magnet simply moves through it. And you see that if depending on the orientation of the little magnet, it will be deflected upward or downward or not at all. No? Simply depends in which direction the tiny magnet was oriented. So that means how much the tiny magnet feels this big magnetic field. If I take an electron, then I see that the electron will be deflected upward or downward. Yeah, and I have thousands or millions of electrons. They all show up at two lines which are at an equal distance from the midplane. So either on the upper part or the lower part, nothing in between. Yeah, and you can see the electrons can be seen as little magnets on one hand. On the other hand, if we can go back, that's actually a good question.
It's
the fourth tab, was it? Okay. Do I see a fourth tab? Yeah. Okay. So I explained that practically quickly through. It was supposed to be some small animations, but now you have seen the total animation, the original one, that are simply split in a few parts, so it's easier to follow. But what we have seen is simply that we had these tiny classical magnets, yeah, which were deflected depending on the magnet orientation, on the orientation of these little magnets. as you know, South Pole and North Pole. So if it's oriented in such a way that the North Pole is upward, yeah, then it will move upwards. If it's in the opposite direction, yeah, then it will move downward. And if it's horizontal, it will be in the middle and then anywhere in between. However, from electrons, we have seen that they are deflected either upward at one line or downward at one line. Yeah, that is some very different behavior than a classical magnet. So the electrons behave like tiny magnets, but a beam of randomly oriented electrons or spins are deflected in two different separated beams at same distances above the midplane, as I mentioned that before, above and below the midplane. So the electrons are not only tiny magnets, but the strength of their dipoles or the magnetic force, the so-called magnetic moment, yeah, of the electrons is discrete. It always is either up or down. Yeah, it's no matter which orientation the electron has. So I want to continue a little bit with that, with doing a few more of these experiments. So the first one that we had seen before was one where we had a deflection in the z direction or in the vertical direction. Now I take another second magnet there in the vertical direction. And that looks like that I first have a source that is here in black on this picture with randomly oriented electron spins. Then I have a magnet which deflects in the z direction. In the next step, I dump the lower part, so the downward deflected beam. So I simply remove them, put them on the screen or in some box, and only look at the upward deflected beam and send this upward deflected beam in a second magnet, which is also in the z direction. Yeah, and what I see at the end, there's only one beam coming out there, only the upward deflected beam. There's no downward deflected beam. So what happens if I rotate the second magnet horizontally? So I'm not measuring anymore in the vertical direction, but now I put it horizontal. So I expect two separate beams, one to the left, one to the right. And that you see actually in this picture over there. And what happens if I take another vertically oriented magnet there? So then I see actually that although in the beginning, I only took the upward deflected beam and sent it through the remaining magnets, at the end, I still have two beams and that means one beam is upward deflected, one beam downward deflected. Yeah, so practically you could say I recovered my original setup, which had two separate beams. Yeah, okay, so that we want to see what it happens, yeah, when we go to the horizontal. So here we have our first magnetic field. So this randomly oriented electrons in the source are sent into this magnetic field. They are separated in two distinct beams, upward and downward. The downward beam is dumped. And then I put a horizontally oriented magnet afterwards. I got two beams out in the X and Y, in the positive, or let's say to the right and to the left. And then in the next step, I've taken another magnet. So I dump again the leftward or the negative X direction. That means I have only one beam left. So this is X plus, or the deflected beam to the right, and send this beam into another magnet, which is in the Z direction. And strangely, what we got out here was, yeah, that we had two beams at the end. Yeah, so one in the positive or one in the upward direction and one in the downward direction. That means we recovered practically the original setting. Yeah, which is not possible if you have classical stuff. So if it's one in one direction, yeah, then if you have magnets which are only oriented upwards, send them once more into some other magnet or make another measurement here of your magnetic field, then it will be still in the upward direction. So the only way to explain this strange behavior is actually that the electron spins are in a so-called quantum state. Yeah, so the magnet or practically any experiments that we are doing will project out directions. Yeah, that means they project out the so-called eigenstates of the system. And here we have only two possible eigenstates, either deflected in so-called positive direction or negative direction, which may be up and down for a magnet in the z direction, or right and left for a magnet in the horizontal direction. So we name these two states, up and down. They are usually named up ket and down ket. And we have seen that if we take only the positive z state, so the up ket, then we saw that if we do a measurement in the horizontal direction, yeah, then this is actually split 50-50 in two separate beams. So either the one to the right or the one to the left, which I've done here in arrows. That means you can write down the upward ket as a combination of a left and right ket. Yeah, and we can do actually the same thing again if we now in the last experiment took the horizontally deflected beam to the right, that means this X plus beam, and send that into a magnet which is deflecting in the vertical direction, then we saw that we got out actually two directions again, positive and negative. So that means we can say that the right or the deflection to the right, the positive X ket, can be also written down as a combination of up and down ket. And in principle, we could change the whole experiment a little bit around and simply dump the X plus and the Z plus directions and only look into the negative beams, separated beams, and we would have gotten actually also at the end 50-50% split out. So there's no difference really. So with that in mind, we can revisit the SG experiment, and now I'm doing practically already quantum mechanics 101 without talking about wave functions, because it's actually not necessary to do that. It's more elegant actually to do it in such an algebraic way. So if we rerun the SG experiment and take into consideration this new phenomenon or this new way to explain these systems by up and down ket, right and left ket, yeah, then we can simply put it this way. Psi is typically used in quantum mechanics to describe an arbitrary quantum state. And any quantum state can be written down in a linear combination of up and down ket. Yeah? So if it's 50-50, that would be easy, but it can be any other numbers here, A and B, arbitrary. So, and then the magnet in the Z direction does a measurement, yeah, on this specific ket. So for that, we got out at the end, you have seen that the original arbitrary ket psi could be written down in a combination of up and down kets. Now, after dumping the Z minus beam, so the downward deflected beam, what we have left is only a ket which is going upward. Yeah, that means at this point, psi is in the upward direction. If we have now another measurement in the X direction, then we have to do the following. We write down the up ket as a combination of the eigenstate or the only possible deflections for a horizontal magnet, which is right and left. So we have to write down the up ket in a combination of right and left ket. Yeah, and that I've done here. So this n, the normalization factor, is not important. What we see here is simply that we do now a measurement in the x direction, because we had initially the up ket was written down in a combination of right and left ket. Yeah, therefore, we get at the end, after the measurement, also these two kets out that we have here in these directions. So if we do the last experiment where we had an additional magnet in the z direction there, then we can look what had happened here. So I go back to the x measurement. So the z measurement is, we have seen already before, the x measurement as well. So what we got out at the end is here, we dump the x minus beam, or the leftward deflected beam. So what we have left is only a rightward deflected beam. And when we do now a measurement in the z direction, then we have to write down the right ket, yeah, or the x plus ket, as a combination of the eigenkets or the eigenstates, yeah, of the z system. Yeah, the z system was the eigenstates were up or down, no, for this magnet. So we write it in this direction because we do a measurement in the z direction. That is my input, and obviously you get both beams out, because you have seen that the input state had actually up kets and down kets, not only one of these. So you can imagine that in case that I have, instead of a second magnet, a measurement in the x direction, I have a measurement in the z direction. Yeah, then there is, as input to this measurement, would be only a ket or a psi, a state, which has an up ket. Yeah, so that means at the end, you get only an up ket out, because there was no component of a down ket there. So that's my experiment. Okay, now to visualize that a little bit, often it's used the Bloch sphere. Yeah, that is maybe, I don't know whether you ever heard about it. So spins can be oriented anywhere in a three-dimensional space. Yeah, not only along the x or y axis, but I said in the beginning, the arbitrary spin orientation or arbitrary ket that I have originally can be in any direction. So we denote in quantum computing the up ket as a 0 ket and the down ket as a 1 ket. And we call these not electron spins, but qubits. And saying that the spin can be pointing anywhere in the three-dimensional space, but taking into consideration that you have to normalize the system. That means all these vectors that describe the orientation of the spin have the length 1. Therefore, the tip of these vectors are all on a sphere. Yeah, and as I've written that down, you can write that as a combination of A times the 0 ket, the up ket, plus B times the down ket or the 1 ket. And the normalization is actually A squared plus B squared is equal to 1. So A squared describes the probability to measure the 0 ket, and B squared is the probability to measure the 1 ket, the down ket. So if you compare that to classical probability, yeah, let's say tossing a coin, no? Then you have either head or tail. So these factors that you have in front, A and B, they are actually added directly to 1. Yeah, so A plus B is 1. So you have either up or down. Okay, in quantum mechanics, you have also either up or down. Yeah, but the probability is calculated in a different way. So this would be the so-called Bloch sphere, where in the upward z direction, so this up ket is called 0 ket, the down ket is called 1 ket, and then you have combinations of these in the horizontal direction, and you see some strange character there, this I, which is used for imaginary numbers, because the problem is the quantum system, so this spin system has only two eigenstates. There are two possible states, up or down, yeah? 1, 0 or 1. However, the spin can be oriented anywhere in a three-dimensional space or on the sphere. So if I take only real coefficients, then I have only the possibility to have coefficients in the spin in the z direction or in the x direction, but not in any other direction. That means if I do a rotation in the horizontal direction, yeah, then, and I get a component which is not in the exactly in the x direction or minus x direction, yeah, then I need some other coefficient or some other system that I take into consideration so that I have coefficients which actually allow that. You see, that is a little bit the difficulty with quantum mechanics. Quantum mechanics is practically some theory where the particles or the waves are moving in complex spaces, not in real spaces. The real spaces is a projection, is what you get out, a 0 or 1. But internally, the system can be anywhere, and it's living in some imaginary complex space. Another thing which is actually interesting here is, maybe you remember from a long time ago, somewhere in math, you did, let's say, algebra or analysis of three-dimensional systems, So if you take simply a standard three-dimensional system, you have, let's say, a z-axis in a vertical direction, as I use that. Then you have an x direction, which is horizontal, and you need another vector, which is going, or another direction, which is perpendicular to the x direction, but also in the horizontal, but 90 degrees off. So if you look here at this system, so if you take your real system, then we say the x and y axis are perpendicular to each other, and also the y and the z axis, or the x and the y axis. So if you look at here, then you see also they are perpendicular to each other. But what happens if I go instead of positive z to negative z? Then I'm actually not changing a direction. Then I'm still moving in the x direction, in the z direction, sorry. However, in quantum mechanics, the 0 state and the 1 state are perpendicular to each other, but they are at an angle of 180 degrees, not 90 degrees to be perpendicular, or we'd say that orthonormal or orthogonal. So it's very different from a classical system or real, vector system over real numbers, meaning that if you work in a complex space, then directions which are perpendicular to each other or orthogonal are actually 180 degrees off. Sounds strange? The other strange thing is actually if we do a full rotation, from the 0 state over to the 1 state and back to the 0 state, then we need actually 720 degrees to do that, not 360. This is coming out of this complex environment. So now I want to go to, after I hope that you understand a little bit what the difference is between a quantum system and real system. So in the next part, I want to go to quantum gates. So we have seen already qubits is practically a quantum system, which has eigenstates of 0 and 1, up or down, like the spin. spin is actually one possibility to construct a quantum computer looking at the spins of electrons. In order to manipulate these qubits, we are using quantum gates. So we have, for instance, the so-called Hadamard gate or H gate. And what it's doing is actually rotating the cat. Rotating the cat, which is, for instance, upward, the zero cat, in the x direction. No? That means to the horizontal. So it's a combination. The one cat is also moved to the horizontal, but in the minus x direction. Then we have, for instance, the x gate. The x gate would be actually moving the zero cat to a one cat and the one cat to a zero cat. That means it flips practically the spin if you have an electron system, or flips the qubit. And that corresponds obviously to the NOT gate in a digital logic. So if you have the standard computer logic where you have ones, zeros, and ones, 0 and 1 here means that you have a specific potential or voltage in the system. So a voltage, you define a threshold, and everything above it is, let's say, 1, everything below 0. That is a classical system. Of course, you optimize your electronic in such a way that the threshold to 1 and 0 is not simply one line, but it's a range. So that means there's not possible that suddenly a number 1 becomes a 0 only because the computer gets hot. Of course, so let's do this, apply the X gate, was actually simply flipping over. And in general, there are several ways to do these rotations or do these transformations. And okay, that's obvious because if you have a rotation on a sphere, then you can do that in the different directions. So you can go straight forward and do a rotation, but you can do also some other rotation and come back to that. So this is an example for that. And that is very often used in quantum computers, because quantum computers are systems. They're using, for instance, spins, but they don't have actually the possibility to rotate the spin in all directions, only specific combinations. So instead of doing, for instance, let's say here an X, so flipping the spin from up to down, they would rotate first the spin around, and then do a transformation and then go back in order to come to the correct result. This is necessary. Okay, let's go back to the magnets. So sometimes you don't have all combination of magnets, X, Y, Z direction, etc. But you have only a few magnets around. And then you have to find some combination of these magnets to get the same result. So that makes actually the whole thing complicated to do calculations. However, in most cases, when you are using software, let's say Qiskit or Cirq, then you are actually not required to know exactly how the quantum computer is rotating really, but you use simply the standard gates. But take into consideration that some quantum computers need, for instance, for one simple standard gate, need, let's say, 5 gates or 10 gates. That means at the end, it's doing a lot of rotations and manipulations in order to get to the result. And having that said also takes into consideration that sometimes the result is actually not what you expect. It's a little bit off. Why? Because it had to do so many manipulation of the qubit. Instead of a single manipulation, it has to go through a whole chain of manipulations. And at the end, the result might be a little bit off, a few degrees off, which is actually important because you don't get the result out that you expect. That's the problem with it. So the other part that is used in quantum computing, or the other principle of quantum system, is so-called superposition or interference. And related to that another piece which I will come to. So superposition you have actually also for waves, yeah, sound waves or light waves or microwaves or anything else. If you have several waves and want to figure out what is the sum of these waves or what is the resulting waveform, yeah, then you have to add up simply the amplitudes at each individual position. Yeah, so here, for instance, you add up the amplitudes, you see that the blue and green wave have actually a different frequency or different wavelengths. And the red waves, the sum is actually not anymore a simple wave, which like a sine wave, yeah, but it's a wave which goes up a little bit, then goes high up, goes far down, and then has a little amplitude, and then goes up and down, very high and low. So this phenomenon of superposition results if you have, for instance, a double split, or you have some object in your wave path, results in interference. Yeah, that is the interference picture that you often see when talking about or when playing around with, let's say, water waves or sound waves. You have that as well. Of course, also with light. Yeah, so the electrons show actually the same phenomena than you have for light waves. They also, if you send electrons on a something like this double slit or a single slit, then afterwards you see actually an interference pattern. Exactly the same as if the electrons were actually light. Yeah, and light in quantum mechanics, we call light photons. Photons is practically the pseudoparticle which corresponds to light. So the last piece that is used for quantum computing is entanglement. Entanglement means that if I know some properties of one part of the quantum system, then I can infer automatically the properties of the rest of this quantum system, as long as the quantum system doesn't interact with the environment. So as an example, and that happens very often, that you have, let's say, an atom that splits into two parts, and the original atom had spin 0, and then you have two parts. The parts have spin. For instance, you have helium for that. Then if one particle or one fraction, yeah, of the particle that decays has the spin in the right direction, then the other one must have it in the left direction. Why? Because the sum of it has to be 0 as it was in the beginning. Or they could show up and down, but they have to be in the opposite directions. So we can use that, actually, this behavior, by moving these daughter particles apart. And still they show up, let's say, for the second part, one in the upward direction, one in the downward direction, because the sum has to be 0, as long as they don't interact with matter around it. So as you know, even in air, we have lots of molecules. Yeah, so typical thing for molecules is something like the tip of a needle is roughly billion times billion times billion molecules. That means for a quantum computer, you have to remove practically all molecules. You have to have a very good vacuum, because otherwise these separated particles, maybe electrons, maybe some other pieces like ions, which we use here often at UMD for experiments, if they interact with the surrounding material, then the entanglement gets lost. So the nice thing is, if we measure the spin orientation or some value, let's say we measure qubit to be 0, and originally we had 2 qubits which were entangled, then the other qubit, okay, depends how we set up the system initially, but I know exactly what the value of the other qubit is, yeah, depending how I set up the system. So if I set it up that originally they have the same orientation, these two qubits, so 0, 0, for instance, and I measure 0 for 1, then I know that the other one has also 1. The specialty there is actually that if I rotate now one of the qubits, yeah, which is apart from the other. So if I rotate, for instance, move this here, flip the spin to downward, then instantaneously the other one will move upward. Yeah? Which is nice because the total system still has to have 0 spin. Yeah, so that means you can manipulate this one here and automatically manipulate the other one, although they are not directly, yeah, located together. Yeah, they can be far away, theoretically, at the end of the universe. Yeah, practically it's not possible because you have too many particles even in the universe. So, okay, here's some pieces don't work correctly. So the other gates that we are using in quantum computing, the so-called multi-qubit gates, they are all based on a controlled manipulation of the system. So the idea behind is simply that if one qubit is in state 1, then I manipulate the other qubit. If the control qubit, so the first qubit in state 0, then I don't do anything with the other qubit. Yeah, with that, I have the possibility to steer practically the system. Yeah, and you can do actually quite a lot of things with it. Here's an example for the controlled X or controlled NOT gate that is very often used. Yeah, that allows to flip the spin of the second qubit depending on the orientation of the first qubit. You can also apply a Hadamard gate in front. So the Hadamard gate was a rotation from the Z direction to the X direction. That means it makes a 50-50 mixed states. Yeah, if remember the positive X direction ket could be written down as a combination of up ket and down ket. And that was a 50-50 probability on both sides, which means here that if qubit 1 is in state 0, so qubit 0 after the Hadamard has 50% 1, 50% 0. And if qubit 1 is in state 0, then the result will be a mix of 50-50 of 0, 0. That means both qubits are in 0 state or both qubits are in 1 state. I hope you understand how it works because the first one has 50-50%. So that means 50% it's up and 50% down. It's the second one. So every time when the first one is up, then the lower one, so qubit 1, will not be changed. Yeah, that stays at 0, excuse me. No? So you have 0 and 0 at the result. If the first qubit, qubit 0, after the Hadamard is in a down state, so it has a probability 50 to be up or down. So if it's in a down state, then this control Z or control NOT gate will flip the spin of qubit 1. That means instead of facing upward, it also faces downward, and both will be 1, 1. That means for this case, we have the result either both are 0 or both are 1. If qubit 1 is in a 1 state, yeah, then you have practically the opposite direction. So that means if qubit 0 is in a 0 state, then the controlled X gate will not change anything. That means you have at the end a state 0 and 1 because the qubit 1 was in a 1 state. If qubit 0 with 50-50% probability is in a down state, so a 1 state, then the qubit 1 will be flipped. That means the opposite direction, and you have also 1 and 0. Yeah. So the result is 0, 1 or 1, 0. Hope it's clear. So the nice thing with these entangled states, and this is a very simple example, you can put another control X gate for a third qubit, and then you have an even more controlled system, which allows you to work as a whole with a complete quantum system, which has many more possibilities than only a single qubit. So quantum teleportation uses actually this fact. And there I suppose that I have a Bell pair, which is shared by two persons, Alice and Bob. It's a typical thing in physics. So it's always ABC. Alice can use her entangled qubit to teleport the state, so the information that she has with the third qubit. And Bob can figure out at the end what is the state of the third qubit. But no one else can figure that out, because the requirement is that Alice and Bob have to have at least one entangled pair originally. So that means this Bell state, as we see that. So that means they have an entangled qubit. Alice and Bob both have one entangled qubit. Then Alice can use additional qubits in order to get the information over to Bob, and Bob can figure out what it is. So, because the nice thing, as I mentioned before, was simply that the entanglement is still there when I split these two parts of the original quantum system. So the prepared qubit I named psi, and it can be prepared in any way as Alice wants it. Alice will do a measurement on her two qubits that she has. So that would be the one part or the component, the entangled component qubit that she has from the Bell pair plus her prepared qubit, and send simply two classical bits, so which have only 1 or 0 as a result, to Bob. And Bob can use this information in order to get out what was the original setup for this qubit. Yeah, and this qubit, this prepared qubit psi doesn't have to show only in the X or Y, in the 1 or 0 direction, but it can go in any other direction. So you need 3 qubits, and then you need 2 conventional bits. And obviously the conventional bits can be simply sent via internet. So it's a completely secure system. Why? Because if anyone moves in between and gets, for instance, the information, yeah, these 2 conventional bits that are sent via internet, and simply copies them, yeah, cannot use it at all, because this third person has to have also an entangled qubit with Alice and Bob, and that is not possible. So teleportation, how it looks like on quantum computer. Sorry that I cannot show that, because unfortunately I had to switch a laptop, and this laptop doesn't have Qiskit or Circ on it, which I need actually to transfer the information to a real quantum computer. Okay, here you have the situation. So first we have an Hadamard gate on and control Z, control X for this pair, that A and B pair. So then Alice prepares the payload and then entangles this payload with the Bell qubit that she has from the original Bell state or qubit. So as soon as she entangles anything with her entangled qubit, then automatically the qubit that Bob had, which was far away, will change its orientation depending on what Alice is doing there. Yes, which is the strange thing in quantum computing. So as I mentioned before, Alice measures simply her 2 qubits. And as soon as you do a measurement of the qubits, the measurement can be only 1 or 0 with some probabilities. but nothing in between, because we have seen that as soon as I do a measurement on a quantum system, yeah, then I get only results out which corresponds to the eigenstates of the system. So for this case, 0 or 1. For the spin case, I had up and down, yeah, or right and left, depending in which direction I'm measuring. So that means at this point, Alice destroyed her qubit system. But the qubit from Bob is still in the state before the measurement. Yeah, that means it still practically has all the information of the entanglement of all 3 qubits together. Yeah, and that is a nice thing. So if when Alice sends her results from the measurement, which can be only 1 or 0 for either of these 2 measurements, yeah, then Bob, depending on the result of this measurement, can simply decide what he has to do on his qubit in order to get exactly the same state out that the originally prepared qubit P had. Yeah, so practically at the end, after looking into these combinations, so depending on the result of these 2 conventional bits, 1 or 0, he does then an X gate or Z gate or both. And at the end, yeah, the third line at the end will have exactly the same state, the same orientation, same probabilities as the P qubit that I had on the top. Yeah, that was Alice's. So in different words, he can get exactly this information out. And the nice thing that I said before, it's only possible to get this information exactly if you have an entangled quantum system. So if anyone else is stealing or copying the information of the 2 conventional bits, which is easy to do, as you know, on the internet, yeah, then it doesn't help at all, because this person doesn't have exactly a qubit which is entangled in this specific way as Alice and Bob are doing it. Okay, so qubits can take any value on the Bloch sphere, and in contrast to binary states, which only takes the values 0 and 1. So if I do a measurement of a qubit, then I destroy the quantumness of the system. And as a result, I get only a projection either to 0 or to 1. And the probability that I get a projection to 0 is simply given by the squared of the coefficient of the up ket or the 0 ket. If I work with multiple qubits, then all multiple qubit systems work in a superposition, so they have interference effects, but I also can entangle them. And it's not possible to copy these informations. So that is a very important thing. That means teleportation is actually a very good example how to get an absolutely secure communication channel. Yeah, so anyone who tries to copy or extract the information destroys the qubit. So here we have the combination here. So this Eve or evil, or okay, whether it's male or female, can steal some qubits out of the channel, but it cannot decrypt the information, because the qubit that it gets simply out of the channel will be not entangled in the same way as Bob and Alice have done that. So nice, secure way. So in principle, the idea was actually that I simply show a short notebook where I run through a few examples and run the same thing simply on the IonQ machine, which is something like a few hundred feet from here. Unfortunately, that doesn't work now, but if you are interested, you can always send me an email and I will simply send you a notebook as a starting point. and some more information and also access to IonQ's machines. Okay, that's for now. So any questions? Yeah.
So then myself, people say that in my crash in normal encrypted system because you can resolve the password that's stored in the bank. The system, like they can resolve like the password.
Yes, okay. That is actually, so what I've shown is simply that you are working with superposition and interferences, yeah? So there's actually something which is called quantum Fourier transform, which is actually using this superposition and interference and actually has also entanglement involved. And that allows you actually to do a very quick Fourier transform, so you get specific frequencies or specific values very quickly out. And that you can run on a very large integer. So the passwords I only can get if I know how the password was encrypted. No? So if you have it simply on your laptop, then it's very easy to get. Yeah. So if I have a spyware on your laptop and simply can get each character from the keyboard, the ASCII number, yeah, then I easily know your password, obviously. No? But the encryption allows, the encryption is actually an XOR that you are doing with a large chain of zeros and one, yeah, or large integer. So the crucial thing, of course, for hacking anything is actually how can I figure out what this large number is, yeah? And in many cases, it's very easy to figure out. So for instance, sorry that I bring this example over and over. It's Windows had actually the problem until, even with Windows XP. Yeah, so only Windows 8, Windows 10, the newer versions are much better. The old versions had actually a very simple encryption system. It's very easy to hack. Why? Because they used a very simple principle. They had some little calculation and then moved all characters by 13 characters away. Yeah. Of course, if you know it's by 13, you can move it back and then you have the original number. No? That was the way as I usually got my licenses, yeah, for Word or so out. No? So I don't like to pay for the stuff. But you can do that actually with even more complicated system. Yeah, a friend of mine who got easily into Pentagon. Yeah, why? Because they don't have an absolute secure system. Of course, they have a comparatively good system, and our laptops are rather poor compared with that. But nonetheless, it's not absolutely sure. So a quantum computer right now is actually doesn't do very much. You can do very simple systems, but let's assume that you have a few 100,000, so roughly 500,000 qubits on a quantum computer, or you could do actually 5 quantum computers and work together with this thing. So the nice thing with a quantum computer is if you work with classical computers, have 2 classical computers and connect them together, you double the power of these computers. But for a quantum computer, you actually exponentially increase the number. So if you have 10 quantum computers or even 10 qubits, then you have 2 power 10 combinations that you are working simultaneously on. And that gives you actually the power to do that. Yeah, you understand? You have 2 power 500,000, no? Which is a really big number. Yeah, and you never can get this number out with a supercomputer. So for this example, if you want to calculate, let's say, an RSA 1024, so one of these nice long numbers with more than 1,000 bits, which are used for encryption, and it's a very secure encryption. No one can actually, we can actually figure it out, we can hack it. But right now, the hacking takes roughly on the fastest supercomputer in the world, roughly 1 million years. Yeah, so it's a little bit long, no? For this little number that you can change the next day. But a quantum computer can, so right now they can't do that, but if they have 500,000 qubits, then they can do that with roughly 2 or 3 hours. Which means you have to change your password very quickly, no? Because a quantum computer will have decrypted it. There's a way around it, which we are trying right now or working on it, is actually that we use not 1,000 or 2,000 bit systems as a large number. So 2,000 is already really a large number, yeah, for a system. But we are using, let's say, a megabyte long integer. No? Then a quantum computer still needs a lot of time, no? Because it's such a big number. So you can make it more secure even with the classical system. But you see the difference when you go in, when you work on very specific problems, then it's possible that a quantum computer can speed up the calculation by very large factors, yeah, exponentially. So that would be an example. Other things where you try to do that, if you have a complicated machine learning problem, yeah, then the complexity goes exponentially with the number of parameters, yeah, and the big systems for, in particular, on natural language processing that we are using nowadays, or on image processing, very similar to that. So language and image processing are using of the order of 10,000 to 100,000 parameters. So very complex. A quantum computer actually can work that simultaneously because it simply can interfere all between these different states. So it can calculate these things much faster. Okay, enough said. Yeah. Yes. Okay, that is actually the problem here, is that we have a complex system. So if you have real numbers and you do a rotation to perpendicular or orthogonal, yeah, if you do an inner product or calculate the x times, let's say x times the z vector, no? Then you get actually, or the projection of the z vector to the x vector, it's the same, yeah, as the inner product. No? Then you see that the length is 0. No? Because if you do here projection, then you have cosine this vector here as the projection, yeah. But if they are perpendicular to each other, it's 0. So for a quantum system, if they are perpendicular, if they're in the opposite direction, then the inner product is 0. So that causes actually that a full rotation is not 90. So you see I have 180 degrees. So if you do a full rotation, so if you do a rotation in a real system, you have 90 degrees, it's perpendicular, then you go 180 degrees, 270 and 360. Yeah, and here you go 180, another 180, another 180, another 180. Yeah. Okay. Good. So.
We're out of time.
Yeah, right. I know.
Any other questions?
So simply write me a mail if you want to have this notebook to play around with as a starting point. That's up to you.